All right. Well, thank you for coming this afternoon. This is Rob Kutrick, CTO here at Cycle Computing, and I'm here to talk to you about, why are you not using public clouds for your big data, big compute workloads, your HPC workloads? We here at Cycle, kind of the driving belief behind the company is that access to compute facilitates new science, better science, and that kind of drives progress overall, making all our lives better and kind of advancing the state of the art. And currently, the cloud is the way to provide access to compute. That is, the goal of Cycle, and that's what we believe. And therefore, it drives what we do, which is trying to make computing in the cloud productive at any scale. By any scale, I do mean any scale. 32 cores, 3,200 cores, 32,000 cores, and up. We focus on enabling that access to help facilitate science and drive things forward. As part of that, we talk to a lot of different customers. We talk to a lot of people in all kinds of industries about the cloud, about access to compute, and the problems that they have. And often when we bring up public cloud, or even private cloud, we will hear the following excuses or reasons as to why people are not investing in that. And that is things like, I already own infrastructure. Or it could be the cost. Moving to public cloud is too expensive. It could be security. We don't trust our data. We don't trust our compute to go over public internet or be running in someone else's data center. Data inertia. We'll often hear from people that have huge data sets that they process in the petabytes, and that it has inertia to it in the same way that a large volume of water or a large physical mass does, getting it to and from the cloud. Physics is what physics is. They may have a customized workflow. They'll say, look, we run MPI, we need low latency, or we have a big data workflow, or we require GPUs or FPGAs, something that they either do not know the cloud providers provide, or that they've already invested in internally. Or the last one that we often hear, less so now than in previous years, is that cloud is just too hard. They already have too many problems and too much work to do maintaining internal data centers and internal compute. They do not need to add that complication into their system for what they perceive is not enough value. And we hear these from three main perspectives. We hear it from the end users, we hear it from the system admins that support those end users across all the divisions and lines of business, and we hear it from the organizations as a whole, the C-level, et cetera, trying to facilitate what their IT admins and what their end users are doing. Why is being productive in the cloud hard? Well, from an end user perspective, it's very easy to get a cloud server. Anyone can go to AWS, Google, Azure, et cetera, and spin up servers, even a number of servers. The problem is actually it's hard to create a workflow. It's hard to get the entire system working uniformly and efficiently and cheaply. And you need your data in the right place at the right time to facilitate that. You need to be able to operate on the data that your calculations require, and you need to handle the data that those calculations produce. And often when you have essentially grown up using a fixed infrastructure environment or limited compute, that's the mindset that you're in. And so if you have access to 1,000 cores or 10,000 cores, you tend to scale the problems you have for that environment. So you kind of quick reject problems that are too large or too difficult or too maybe low priority. And you tend to use algorithms that are optimized for that environment. So learning to adapt to zero queue times, learning to adapt to unlimited scale can take some time, and it can take some mind shifts. And then, once you've even done all that, you have to understand your billing, and you have to understand your usage so that you don't get any nasty surprises, and you can kind of optimally get the compute for the price that you're paying. Then you have the sysadmin perspective, and the individual users have their environment and their tools, but the sysadmins have to support many users, potentially many lines of business, and that means many workflows, many software suites that they then have to onboard. They have the same data placement problems, and then they actually usually have the additional problem of data security and data access, making sure that only the right users can access the data. And then once they've started providing these services to the internal compute people, they have to simply grow that user base across the entire organization and then support them. And then a similar mind shift happens for the IT staff. They now have access to essentially disposable resources across cloud providers or even within a cloud provider. And that is a different mindset for management and reporting and using than when they had fixed infrastructure inside of a data center or data centers. And finally, from the organizational perspective, being productive in the cloud is hard. There's security concerns, especially for regulated environments, validated environments, or even just extremely sensitive IP. You want to make sure that only the people that are supposed to be seeing that data, supposed to be seeing those algorithms, and supposed to be influencing those environments are. Then you have the expenses and budgeting. The individual user worries about their own bill. Well, the organization, you're worried about the bill across everybody. And so that is definitely something that throws up roadblocks for a lot of organizations. And then you have just the complexity of managing this environment and managing the usage across a single cloud provider, across multiple cloud providers, and in a hybrid environment between your internal internal compute and the external compute that you're granting access to. And enabling that so that it's actually empowering for your users and efficient for your organization as opposed to yet another roadblock. And this is the same set of problems from those three perspectives, no matter what kind of workflow you have. So if you have a traditional HPC workflow, which I've heard people describe as small data creating big data, you're going to have those same sets of concerns. It's still access to computing power. And then if you have kind of one of the new hotness workflows, you're running a big data workflow, you're doing analytics, you're doing machine learning, et cetera, it's been described as big data creating little data. It's still the same access to compute problem. So given all those roadblocks and given all those reasons we hear from across industries as to why you would not use cloud, who is using it for HPC workflows? Well, pretty much everybody in some way or another. So we see users in finance, they're doing batch processing, traditional stuff, risk modeling, Monte Carlo simulations, back testing trading strategies, you name it, people in finance are using public cloud. We're also seeing it in a lot of the new analytics workflows, people with Hadoop clusters, Spark clusters, Cassandra environments, Mongo, et cetera. Everything from log processing to kind of advanced machine learning. And then in life sciences, genomics, proteomics, molecular modeling, CompChem, PKBD for clinical trial simulations, across the entire swath of life sciences, we are seeing public cloud usage in every facet. And then in manufacturing, oil and gas, simulation, design, et cetera, people often write those off as traditional MPI workflows, but we are seeing people run those in public cloud, and very effectively and very efficiently, as we'll touch on. So one use case I wanted to highlight in particular is NASA. Now, NASA won Intel's Head in the Clouds Challenge Award, and this was specifically to estimate biomass in South Sahara in Africa. And the idea was they were taking NGA data, so satellite data, and they want to automatically process the images to get an idea of basically vegetation in Africa in order to estimate the carbon sink of that particular area. And this was for climate change research and climate modeling. And this was done by Dr. Tucker and Dr. Morin, and it is building on previous work that they and others have done. Now, this is the entire area that they wanted to study, this entire swath of Africa. And so as you can see, anyone who's familiar with the continent, that is a huge amount of land that they want to take satellite imagery for and process. So you can imagine kind of the data set size is getting quite large. And how do they break down that data? Well, you can see right here. They broke it down into single UTM zones, which are still quite large, being 658 kilometers by 1,300 kilometers, roughly. They took those zones, they break them into tiles, they break those tiles into subtiles, and then finally they create chunks. And the chunks are what are analyzed in the public cloud. So the workflow works as follows. You have the NGA data, which is external to the internal NASA data center. They pull that NGA data into their internal data center, their shared file system, which I believe is a Lustre file system. They do the pre-processing there. That's where they create the chunks. That's where they get the data ready for analysis. The cool thing about this workflow is it's event-driven. And so instead of trying to wait until the entire data set is ready to go and processed all at once, they stream pieces up into the cloud for processing as available. And this gives them a much more efficient workflow, kind of a continuous processing. And so as internal jobs are ready, basically, Cycle's Dataman software is notified and transfers those pieces up into the cloud. And so it moves them over here into AWS S3. When the transfer is complete, it fires an event, which then spins up the compute environment to analyze that data. And so this is a very cost-effective strategy, and again, very efficient. And the compute environment is running an HD Condor batch system, traditional pleasantly parallel batch system. And it's using, every instance is basically sucking down the data from S3 for the computation. Kind of an overview again of that event-based model is the satellite data comes into the local environment at NASA. When ready for processing, it is pushed up into S3 as ready. It is then, compute environment is then initialized and spun up and provisioned and fully configured in the cloud environment on demand. The analysis is performed. The output data is then sent back into NASA's internal environment. So for the end researcher, there's essentially just a constant stream of new processed data ready to go. So this environment for these runs had some fairly straightforward technical requirements. They set up the workflow so that it was 1 core per job, just for simplicity. Each job requires about 4 gigabytes of memory. So that kind of tells us which instances can be used inside the cloud. It was a standard operating system, CentOS. Luckily, sometimes when you run things in the cloud, you do come across licensing concerns, but in this case, it was internal software written in Python, so there was no licensing concerns, just IP concerns. Again, it was pleasantly parallel, so scaling this up in the cloud was trivial. It was just an issue of allocating the resources and then configuring it. The total input size for this test run was 8 terabytes, and the total output back was only 2 terabytes, so this particular run wasn't a particularly big data problem, but this was just a kicking the tires run for the full workflow, which is in aggregate quite a large amount. And so what ended up happening was we used the spot market to keep it cost effective. So in AWS, the spot market is eBay or Priceline for compute. And basically, AWS keeps a buffer of compute above the on-demand amount that gives them the flexibility to always satisfy their customers' demands. But those customer demands can be spiky in nature. And so they enable people to get access to compute at a fraction of the cost, with the trade-off being that they might take that compute back from you before you're technically done using it. And so you want to make sure that your workflow is amenable to interruption and to restart, or that it finishes so quickly that the chances of them interrupting you are minimal. You'll never pay more than what you bid. So you basically say, I want to pay 25 cents for this instance. The instance might cost $2 an hour normally, and so you're getting it for a fraction of the price, and then you'll use it for however many hours, and then if interrupted, you don't pay for any of that hour, the last billing period that you were using it. And so for people with jobs that run quickly or for jobs that can be restarted, it's an extremely cost-effective way to get access to massive amounts of compute very easily. And so this entire run that I was just talking about cost $80. And so that meant that in the spot market in AWS, they were able to do an entire UTM zone for $250. They could do 11 of them, which is the entire swath, for $2,700. If you add in the satellite imagery costs and some other processing costs, you get an entire run cost of $11,000, which is just nothing compared to how much it would cost them to provision that infrastructure themselves. And oftentimes, we've been focusing on the compute cost, but people will mention storage. But honestly, S3 storage and other storage costs in AWS are so cheap that they were basically a rounding error on this calculation. And so this proved out this model. And so the goal is to actually turn this into a service within NASA, within NCCS. They have internal compute, they have multiple environments for different kinds of use cases, and they want to give their researchers the ability to burst out into public cloud when appropriate for the workflows that they have. It's just one more way of enabling their users to get the compute that they need to solve the problems they need to solve. I touched on it earlier, saying the inputs to this run were 8 terabytes and the outputs were 2 terabytes, not particularly large, but you can see how that's going to grow. So the entire reanalysis is 400 terabytes. It's a pretty good chunk of change. And now you're up to 1.6 petabytes if you talk about their operational resolution. And that just keeps growing all the way down to the final cloud permitting full goal of 1.6 exabytes. And this is just for sub-Saharan Africa. The end goal would be to do more than that. I mean, imagine the idea that you've actually trying to calculate the carbon sink potential of all vegetation in the entire Earth. Clearly a very, very large data problem, and something that the researchers would love the ability to do using a mix of internal and external resources. And so this is kind of the future of big data and HPC at exascale at NASA. You have kind of 2 dimensions across which You can map your applications and your needs. You have analytics intensive, and you have the computationally intensive dimensions. And there's always going to be a need for internal infrastructure to satisfy those. So the goal is to supplement this with public cloud in kind of a true, efficient and simple hybrid model. And that was just NASA, just this one project, and just the one use case. There's many others within NASA itself, and there's many others across all the industries I mentioned earlier. And so I kind of want to come back to what the original point of the presentation was, which is, why not public cloud for big compute and big data in HPC? And again, the reasons we hear is, I already own the infrastructure. Well, NASA clearly owns a massive amount of infrastructure, and they still find value in using public cloud to supplement it when needed. The ability to say there is zero queue time to certain users is tremendously valuable. Cost, well, using the AWS spot market, using Google's preemptible instances and other kind of cloud provider cost optimizations, you can clearly create very large scale environments at incredibly competitive prices. Security. We touched on this a bit, but I just want to say that the cloud providers deal with security at a scale that very few companies and very few research institutions have to concern themselves with. And it's one of those concerns that you can, in some ways, offload to somebody else. And so let them handle data center physical security. Let them handle preventing actual access to the boxes. Let them handle intrusion detection and kind of inappropriate behavior at a cloud-wide scale. And that allows you to focus your security efforts on your application and your workflow and what you need. And then data inertia. Physics is what physics is. So if you do have huge amounts of data, you still have to optimize, where you're moving it. But clearly, we're talking in the hundreds of terabytes and growing from there. Organizations are finding it useful to push that data up into public cloud. MPI, big data, GPU, custom hardware. Okay, yes, there are cases where the cloud providers do not offer that, but cloud providers are offering GPU. They are offering InfiniBand. They are offering SSD and flash storage, and there's more innovations coming down the pike for that. And so, in some cases, you do want to continue. You want to continue using internal infrastructure for those customized workloads. But the great part is you've made this investment in internal infrastructure, and now you can put the compute that does not need that out into public cloud. And so suddenly the researchers that were sharing an optimized environment with people that didn't really need it suddenly have that optimized environment to themselves. And so now you've reduced their queue time. Now you've reduced the complexity of managing those environments in parallel. And so sometimes the cloud can be a way to offload work that doesn't, kind of the low bar, low hanging fruit work goes to public cloud, and the specialized, really cutting edge science can still stay inside. And then I hope I've shown that for even kind of an event-driven workflow like this, it's no longer too complex. There are not just our software, but there are other things out there that will facilitate using public cloud to the point where I think it's almost an obvious choice. Switching that around, what do these three different perspectives, the scientists, the end users, or the system architects and sysadmins that are supporting them, and then finally from an organizational point of view, what are the real benefits they're seeing from this? Well, the end user, it no longer has to deal with the IT concerns. They have an environment that works for them at a scale that works for them. So your scientists, your quants, your designers, they can focus on doing their science. They don't have to worry about IT. I've worked with scientists before who had written workflow scripts and who had written provisioning and configuration scripts and programs on their own that no longer had to deal with any of that. And they were super excited to no longer be overworked with science and IT. Now they can just be overworked with science. No wait times. So a zero queue time is an incredibly attractive thing to end users. The idea that they have their own environment, their own sandbox to play in, and they get access to as much as their budget will allow is incredibly attractive. And it's simplified access to those resources. So using our software or using other people's software, being able to just push a button and run your jobs and have it all work is incredible to the end user. From the sysadmin's point of view, you're getting programmatic workflows that link the cloud usage to your internal processes. You can do burst, and you can kind of manage these all from a systemic level, and it allows you to provide these resources across the scientists, across the lines of business. And the same benefit from being able to outsource kind of the provisioning concerns and the owning equipment concerns, your IT staff no longer has to spend their time swapping out drives and checking the IB cables and checking the storage and whatnot. They can focus on the IT concerns specific to the workflows that the users are running. And that includes things like cloud service management. They can provide this compute from a single interface and provide it across all the end users. And then from an organizational point of view, you get the security benefits of all the expertise that somebody like Google, somebody like AWS, somebody like Microsoft brings to the table as far as operating these data centers. And you get the ability to more accurately map back the value of the compute to the cost in the cloud provider. So you can look at that run and say, was this run worth $80 for NASA? Clearly it was. Was this run worth $5,000 for another researcher? Clearly it was, or clearly it wasn't. And you can also take advantage of available compute in the different cloud providers, in the spot market in particular, when the price makes sense. So you can actually say, we only want to run this work when it can be run for this cost. So that's something you can't really do with internal infrastructure. Taking advantage of compute in the cloud from an organizational point of view is an operating expense. You no longer have to invest in infrastructure that you then have to own and manage and depreciate. That may not be something that the end user, the scientist, thinks of, but it's definitely something that from an organizational point of view matters. And finally, a lot of times when we come across people that say, yeah, well, we just bought this cluster. We just bought this HPC environment. We just bought this Hadoop system. And it is the latest and greatest, and it is so shiny, and it is so cool looking. And that's great, but 6 months later, it's not going to be the latest and greatest anymore. But chances are, one of the cloud providers has refreshed their infrastructure, and they have the latest and greatest. So if you are able to take advantage of the cloud providers, you're basically always going to get access to the latest and greatest tech, the latest GPUs, the latest processors, the latest storage devices and networking. And then if you are taking advantage of their data centers, you don't have to deal with that anymore. From an organization, if you're a finance company, do you really want to be running data centers? If you are a design company that's doing fluid dynamics and physics simulation and micromagnetics, focus on what you focus on and let somebody else take care of the rest. So I hope I've made a pretty good argument as to why public cloud can supplement internal HPC environments or even be used solely for certain HPC calculations. It is, there are a lot of benefits, and there's these constraints that have been solved, but it is still a hard problem to use the cloud productively and efficiently and cost effectively. And that's where we come in. So us and others like us make software that makes the cloud productive. So you can use CycleCloud and DataMan and our other products to provision, monitor, audit, and scale up, scale down your workflows inside of the different cloud providers, across the cloud providers, and from internal environments into the cloud. And we handle kind of all aspects of that. So it's everything from provisioning the infrastructure, so actually going out and requesting it, setting it up, and that's not just the compute, that's the storage, it's how it's configured. You might want to have persistent storage versus ephemeral storage. You might need it rated a certain way. Maybe you want to run a Lustre file system in the cloud, or maybe an NFS filer is simple enough for you. And that also includes configuring those environments. So great, you've spun up 20,000 cores in AWS or 50,000 cores in Google. You don't want to hand the users those systems as if you had just turned the power on. You need to set them up so they're ready to run. Now they're running. You want to only pay for the infrastructure that you're using, so our software will enable you to auto-scale those environments up and down. It will track the jobs, it will track the workflows, and it will report all that back to the end user so they have a definite sense of control and actual control over the environment, as well as visibility into what's going on at the end user level, at the sysadmin level, and at the organizational level. And then it'll handle errors. When you're operating at 500 cores, you can handle the occasional error, the rare error. When you're operating at 50,000 cores or 500,000 cores, that's a constant process that you need to be automatically handling. And then finally, tearing it all down. Again, the cloud is disposable resources. These are things that you get when you need them and you throw them away. And doing that in an efficient and cost-effective and auditable, repeatable way is something that our software brings to the table. And so basically by handling all of that, we make it push-button easy to add compute for all your researchers. So always happy to talk in much more technical detail. Let me know if you have any problems.